Hi guys, welcome back to Ryan's Study Corner. I am Royan, and in today's video we are finally doing our write-up for the Pendulum Lab. Now, if you have not watched that video yet, then click on the link. I'll attach it somewhere. I have no idea how to do it yet, but I'll do it. I'll figure it out by the time I upload it. So click on that, watch that video, make sure you understand what's going on, and then you could come back to this one to see how to actually write it up. So we're going to go through the whole thing together. So let's get into it. Now first we have our title. Before I forget, if you want this, go in my description box, click on the link, and you will get the essentially, what's it again, the template for how to write up a lab. Print it, keep it in your lab book. It is a big help, so use it however you like, but that is what I used and I edited to make this write-up. So first thing we start off with is our title. I already typed in that, period of a pendulum. Now our aim is to investigate the relationship between period and length of a pendulum. We knew that from our last video. Our apparatus and material. So now I'm going to list out everything that we used for that lab. So I will have my retort stand, I will have my clamp, my pendulum. What else did I use? I used a ruler to measure the length of the pendulum. I used a stopwatch to check the time for the pendulum, and I think that was it. And then we go into the diagram, so that somebody who's looking at this could be able to see exactly how to set this up. People have asked me if you can take a picture and put it. As far as I know, that is not the case. It has to be like a almost schematic, for want of a better word, type drawing. So I have my my retort stand. You all know I can't draw to save my life, so this is as good a retort stand as you are going to get. So this is my retort stamp and my clamp, and from here I have my pendulum bulb. Now you will have a neat and nicer drawing than this, and I'll make sure to label it. So I have my retort stand, my clamp, and my pendulum bulb. I won't include my ruler and stopwatch here since those are pretty much free and I just use them when necessary. Now for the method, most likely our teacher would have given us the method in present tense because we are going to do it. So she or he has just given us clear instructions. We know though that this is not the tense that we will use. So we have to write it in past tense, yes, because we've already done it. But as not so wonderful as it might sound, they don't care who did it. We aren't going to say, Royan did this, Royan did that, and this other, my lab group member did this. No, they just want to know that it was done. So we are removing ourselves from it. So that's why I said the apparatus was set up as seen in the figure above. I can't say I set up the apparatus as seen above. Then the string was adjusted, so the length of the pendulum was 50 centimeters. We know this. Then the bob was displaced slightly and allowed to swing or oscillate 20 times, and the time taken was recorded. Once the bob was stabilized, it was again displaced. So I didn't displace it. It was displaced, and the time taken for 20 oscillations was recorded. This process was then repeated for pendulum lengths of 5 centimeters, 40 centimeters, 35 centimeters, and 30 centimeters. If you want, you could pause this and take this down and just tweak it as it pertains to how your lab was done, because it will be something that was pretty similar. So now I am going on to my results. So I have my results here that I wrote down when we were doing the lab, so I'm going to fill in the table. In most instances, your teacher would show you the table that you're going to do, or sometimes they don't, and you will figure out what has to be put in each of the columns based on what your teachers tell you to measure. So my length here is in centimeters: 50 centimeters, 45 centimeters, 40 centimeters, 35, and 30. Now I am going to convert my length to meters for this. Some teachers will tell you just leave it as centimeters, so you go with whatever they tell you to do. I'm choosing to convert it to meters, and I will have, we know to convert from centimeters to meters, we divide by 100 or move the point 2 places to the left. So I'll have 0. I thought I had blue ink. I'll have 0.5 meters, 0.45 meters, 0.40 meters, and I'll add in my 0 here, 0.35 meters, and 0.30 meters. Now all of my time readings were 30.56, and then T2, as in the second time I did it, was 30.62. Then I have 28.69 and 28.53, 26.94, 27, 24.94, and 25.19, and 23.78, and 23.69. So now I have these readings, I have to find the average of each of them. So this is a precaution that we'll have to list in our precautions. So we took this precaution to minimize error. So in case there was a particular error in one of the measurements that we took, if we find the average, it's kind of like minimizing or spreading out that error, if that makes sense. So I'm going to take my calculator and I will say 30.56 plus 30.62 divided by 2. So let me write the formula here. I will be writing T1 plus T2 over 2. So I get 30.59, and then I do the same thing for the next one. So I'm going to say 28.69 plus 28.53 divided by 2, and I get 28.61. And then for the next one I have 26.94 plus 27 divided by 2, so that's 26.97. And then I do the same thing with all of the values that follow. So now that I've found the average, if we think about it, that average time is the time for 20 oscillations. But we actually have to find the period because we're comparing we're looking at the period of a pendulum and how length affects that. So we have to find the period. Now remember, the period is the time taken for one oscillation. So the average time that we have there is the time taken for 20 oscillations. So if we think about it, if we know the amount for 20 and we want to find for 1, we just have to divide this now by 20 and we'll know the time it took this pendulum to make one swing. So my first value is 30.59. I'm going to divide that by 20. That gives me 1.53, and we know we'll have to do a bit of rounding here. Then 28.61 divided by 20, I have 1.43. Then 26.97 divided by 20, 1.35. 50.13 divided by 20 is 25.8. 2.5, 1. And then 23.74 divided by 20. And that gives me 1.2. I'm sorry if this looks a little bit busy. I probably should have zoomed out a little bit more so that I would have been able to write it a little bit smaller and neater. So now I have to find the period squared. So the same values that I just calculated and put in the t column, I'm just going to square each of them and write it next to it. So 1.53, and notice if I just do 1.53 and then square it, I'm kind of already introducing some error here just by rounding, because I would have had to round to get that, but we'll run with it. So 1.53 squared, and that gives me 2.34. And if I want, I could just do 30.59 divided by 20 and then just square that one time, and I get 2.339. So it's not too bad of an error. So 1.43 squared gives me 2.04. Then 1.35 squared gives me 1.82. 2.51 squared gives me 6.30. And 1.2 squared gives me 1.44. But now as I'm looking at it, guys, I have some big error that I made here because this value is off. What did I do? Ooh, look at what I did. I forgot to divide by 2 here, I think, because that 50 value looks like if I just added these two and I forgot to divide it by 2. So let me fix that. 24.94 plus 25.19 divided by 2, so that's 25.07. And then when I divide that by 20, so let me erase all of this one time. When I divide that by 20, I am going to get 1.25, and when I square that, I will get 1.57. So the values that I really care about are these and these. And notice that my tables have the quantity / unit. We always have to make sure to include our unit. So I have my values here and my table, so my results section is done. And now I have to go into my calculations and interpretation of results section. So what do I do here now? Usually your teacher will give you a formula. In many cases, they may just give you this formula right off the bat. T squared is equal to 4 pi squared on G by L. And what we have to do that here, I'll explain where we get this from just now. What we have to do here is recognize that this is our essentially equivalent to our y value, and this is equivalent to our x value. Because they'll ask us to plot a graph, so let me write that in a different color. They would usually say in our calculation section, plot a graph of, sometimes it may be like t squared against L. It's usually t squared against L, because L is the one that we're changing, and the one that we are changing, or what we are manipulating, which we call the manipulated variable, is usually on the x-axis. So then we could see how the y changes as we change x. So they'll tell us to plot a graph of t squared against L. And if we think about it, that essentially means that t squared is y and L is x. If you are used to the equation of a line, you know the equation of a line is written as y is equal to mx plus c, where m is our gradient and where c is our y-intercept. So if we have y is equal to something by x, it means that this here will be our gradient. So this whole big thing here, 4 pi squared on g, is our gradient. So that represents whatever value we happen to get as our gradient, because we know that's going to be part of it as well. So, but where do we get that from? If you want though, before we go into where we get that from, you could think about it this way. When you plot your graph of t squared versus L, and they ask you to find the gradient, you'll say, well, change in t squared over change in L. Now, if we rearrange this to send L over on the other side, we will end up with t squared over L is equal to 4 pi squared over g. So it means then that literally from that, we could see that this ends up being 4 pi squared on g, just based on the understanding of the equation of a straight line. Now, this whole formula actually comes from t is equal to 2 pi by the root of L on g. So this is actually the equation for the period of a pendulum. But our aim is really just to always try to get things in a linear form so that we could get a straight line graph and pull information from it. So we will end up with this. Now, when we do this and we recognize that our gradient is equal to 4 pi squared on g, then one of the next steps that usually come in this calculation section is to find g. Now, what is g? G here is acceleration due to gravity. We usually round up to 10, but we know it's like 9.8, 9.81. So they're going to ask us to calculate g to see if we get something similar to 9.81. So what would happen now? Let's say that we get a gradient of 4. Now I'm just randomly calling out that value. So if I get a gradient of 4, now you'll get whatever you get. I am just saying 4 because I remember a past paper question I did with my Form 4 physics class one day, and the gradient ended up being 4. So gradient is 4, then it means that I could say, well, 4 technically, 4 pi squared on g is technically equal to 4, because I recognize that 4 pi squared on g represents our gradient. Now, if we want to rearrange this, you could think about this in 2 ways. Now, we know there are multiple ways to rearrange an equation. I like to say, hey, I'm taking this and sending it over to the other side, and when I send it over, it's going to become the opposite, because that's what most of my students understand better. You are probably used to saying, okay, if it's on this side and I want to get it on the other side, I have to think, what do I have to do to this side to get rid of it? And once I figure that out, I know that whatever I do to this side, I have to do to the other side as well. So that's how we get it over. But it doesn't matter, we're going to end up with the same answer anyway. So I'll say I want to make g the subject of the formula. I will send my g over to the other side. And because g is in the denominator here, it means it's involved in division. So when it goes over, it will switch to multiplication. Now I'm going to just erase this here so that I get a little bit more space. So what happens next? It means that I have 4 pi squared is equal to 4g. But now g still isn't by itself. It is here stick up to the 4. So I need to get rid of this 4, so g will be by itself. Now when I send this 4 over, I have to keep in mind that this 4 is being multiplied by g here. So when I send it over, it's going to switch to division. So I will have 4 pi squared over 4 is equal to g. And I will plug this whole thing into my calculator, and whatever I get, that is the value I have for g. Now again, remember, I just use 4 here. You could have gotten 2.5, you could have gotten I don't know what. It's just, rather than making this a really long video where I'm plotting a graph, I just choose a random value. So using that and running with it, if I have 4 pi squared divided by 4 I get 9.87. So G is equal to 9.87. And I know that my unit will be meters per second squared. And I know that too because the unit on my because of the unit on each of these axes. Now I am just randomly using 4 here, and it worked out because the question I remembered is from a pendulum type question, but that's fine. Even if you don't get something close, then that's fine. The purpose of a lab isn't to be, hey, I got the perfect answer. It really is to try all of the practices to actually do the lab, and then you could explain away your answer. Because if you think about it, the things that your teacher is marking is not, hey, you got the correct answer, but it's the process. So if you get 5.6 SG, you just have to explain why. So you explain why in your discussion, you explain in your sources of errors, and you explain in your precautions. So this is my value for G here. Now, different teachers might phrase this different ways. They may ask for some other things too, but generally the norm is plot a graph of t squared against L, find the gradient. Using the gradient now, figure out what G is, and they'll usually help you through it. Even if you don't understand well, just let me know in the comments and I could kind of try to explain, make a next video, we'll see. So this is G, and that will usually be all that we have in our calculation section. Now let's go on to discussion. We always are fighting up and trying to figure out what to put in our discussion, but our discussion is exactly that. We're just going to discuss what we did. So some people put some definitions in their discussions too. If in your school you'll write a theory, then you don't have to put definitions in your discussion. Most teachers don't really care about the discussion in these types of labs because they care the things that they're actually marking, your calculations and that sort of thing. So discussion. In my discussion I will say, hey, well, the period is the time taken for one oscillation, and the aim here was to see how period was affected by the length of a pendulum. And we recognize that the period, if we look here, the period got larger as the length increases. So notice 30 has a period of 1.2, but when we go up we see a steady increase, and when it was at 50 we have 1.53, which means that we could see as our length increased, our period increased as well. So, and the other thing we did was calculate G, so I can make sure to address all of these things in my discussion. So I am going to write a little bit of a mini essay here. You don't have to do this, but I just, for being thorough for your sake, to kind of give you a better idea of what we might come up with, I will say the period of an oscillation is the time of a pendulum. What am I writing? The period of a pendulum is the time taken for one oscillation, or time taken to complete one oscillation. We see that as the length of the period increased, why am I saying the length of the period? The length of the pendulum, guys. Why am I only making the same mistake? As the length of the pendulum increased, the period increased. this was used to calculate the acceleration due to gravity. This value is usually taken as, or the theoretical value of this. So this value is usually taken as 9.81. The value calculated deviated from this slightly due to the errors mentioned below, because you don't have to rewrite all of that here. That's what your sources of errors is for. I hope you all understand what I wrote here, because my handwriting is all the crap over. So right, that is it. Now, well, when I say that is it, I mean for the discussion. But now we have to go on to explain our sources of errors and our precautions. Sources of errors. Now, our sources of errors are those things that we did that caused our value to be a little bit further away from the actual value than we like. So maybe one source of error might be one source of error might be that your eye was not at eye level with the marking when you were taking the reading of the length of the pendulum. So I could say parallax error, because we know that's what parallax error is, when you're supposed to get your eye at eye level of the meniscus or whatever it is you're measuring. So parallax error when reading ruler. Or maybe you might say that you couldn't get the length exactly to the middle of the pendulum, because we know it's not to the middle, it's not to the end of the string, it's actually from the tip of the string to the center of the pendulum. That's what we take as the length. So since you couldn't get an exact space for the center of the pendulum, you can see that that is an error. So the length of, or you could say the center of the pendulum was approximated to find the length of the pendulum. What is another source of error? I remember for some reason when I was doing it, my string was kind of slanted a particular way for some reason. So you could say that is an error. So the path of the bob was maybe not to and fro but slanted, or was slanted when swinging, and you could go on to say that this could have thrown off your values a bit. Another thing that we could say is that we didn't use a protractor to measure the angle that we pulled it back by, so it's very possible that we could have done a slightly different angle every time, even though we know that is not anywhere if we think about the factors that affect the length of a pendulum. But the same angle of displacement was not used for every reading, or maybe you could just say it was approximated. You could go on to say if your table wasn't completely level or completely stable. You could list those things as well. What are precautions that we took? Well, for one, I took two values, T1 and T2. So for the same length, I counted 20 oscillations twice so that we could find the average of them. So the two values, or let me say two readings, maybe that might be stating it better. Two readings were taken for the time for 20 oscillations for each length, and the average calculated. So that's one thing we did. Another thing we did was we used the countdown method so that I could press the timer at the same time that I released it. So the countdown method was used to reduce reaction time error, and I feel like there were some other things that I listed in the video as I was talking through it, but I can't seem to remember them now. So if you all can remember what they are, just let me know in the comment section. Help us all learn. Or if you know some that I didn't mention in the video when I did the Pendulum Lab and that I didn't think of here, then let us know so everybody can know to include it when they're doing their lab. So this is all that could come to mind one time. I also would just comment below if any come to my mind after. And conclusion, your conclusion is really just answering your aim. So you're just saying, hey, this is what we got. When I was in Form 4 and Form 5, I would literally just say the value of whatever was found to be. But when I think was at Cape level or in UE, then I saw people writing really nice things like, within the limits of experimental error, the whatever was found to be. And I was like, this seems nice and fancy, I'll include it. But in reality, like, that doesn't actually affect anything. The conclusion is really just to state what you got out of this, and we know that it's within the limits of experimental error. That's why we have all of our sources of errors listed out here, because we know that these things, as well as other like environmental conditions and stuff, would have caused our values to deviate. But like, you could put whatever you want. If you like it, your teacher likes it, go for it, as long as you make sure to have the information that we actually need there. So I will make sure to say that, because remember the aim of this, if we go back there, the aim was to investigate the relationship between period and length. So I have to make sure to say that. So I will say that, and you could start about within the limits of experimental error, the period of a pendulum was seen to increase with the length of the pendulum, and then the other thing that we did was calculate the value for G, and I got 9.87. So I will go on to say now that and acceleration due to gravity was found to be, what I get, 9.87 meters per second squared, and that's it. So I hope this was helpful, guys. Anything that you're not sure about, anything that you want clarification with, just comment below and I'll be sure to try and clarify. Thank you for bearing with me with my crappy foot handwriting. I really hope this was helpful. And next I'm thinking about doing the finding the center of gravity as a laminar lab. So if you all want to see that, or any other labs that you all want to see, as long as I have the equipment to do it, I'll definitely do it, and probably go through the write-up as well, so that you all can have an idea of what to do in your labs. So that's it for today, guys. Remember, be safe, be kind to yourselves, and look out for the next video. Bye bye.